Hello, Chem 213 students, and welcome to the first video for this week regarding aldehydes and ketones. So aldehydes and ketones are, especially aldehydes, are a functional group that's associated with many nice smells such as vanillin here, which is the primary scent and flavor component here of vanilla. And so let's talk about various compounds that have aldehydes and ketones and the kinds of reactions they undergo. So aldehydes and ketones are defined by their presence of a so-called carbonyl group. A carbonyl group is a carbon double bonded to an oxygen. And you're going to find carbonyl groups in all kinds of biological molecules. And the simplest aldehyde here being formaldehyde, having a carbonyl group with hydrogens attached to both. What defines an aldehyde relative to a ketone is for the carbon double bonded to the oxygen, there's a hydrogen attached as well as a carbon, or in the case of formaldehyde, two hydrogens. Whereas in a ketone, both of the atoms attached to the carbon double bond to the oxygen are other carbon atoms. So formaldehyde is often used as a preservative for biological specimens, for example, the ones you might dissect in your biology class. And acetone is a solvent that we use very regularly in the OChem lab, and it's very nice for washing out water because it dissolves water, washes it out, but then when it evaporates it leaves nothing behind. So it's really great for doing a final rinse on your glassware to get out any remaining water. So we can see here the compound vanillin, which causes the vanilla flavor here, has an aldehyde. It's actually a benzaldehyde group here. We have cinnamaldehyde here, which is cinnamon flavor. It's an aldehyde that has a resonance with the benzene ring here through a pi bond that's in between. So we have alternating pi bonds all the way through, double, single, double, single, double, single, all the way around here. Carvone is a spearmint flavor. R-carvone is also S-carvone, which is the caraway. That's a ketone here. Benzaldehyde is the almond flavor here, just benzaldehyde without these additional groups. So you can see vanillin, the vanilla flavor and the almond flavor have a very similar molecule. The steroid hormones, for example, progesterone and testosterone, also contain ketones. That's the reasoning for the "-one ending, which indicates the presence of a ketone. When we name these, we want to keep in mind that naming in the priority now for aldehydes and ketones, these will be our highest priority group, higher than alcohols now, but it's going to be the same general procedure. We're going to identify the parent chain, the names of the substituents, assign a locant, and assemble the name of the locants, writing them in alphabetical order. In terms of the ending of the name, if you have a aldehyde, the name is going to end with al. So here we have a hydrocarbon with 4 carbons, so its name is butane. Ane for hydrocarbon with only single bonds between carbons. And if we have a 4-carbon aldehyde with an aldehyde here at the end, we end the name with al, butanal. Now remember that the aldehyde group is the highest priority group, so when we decide what the parent chain is, we must include that group. So although here in this example, we have a 8-carbon chain, 1, 2, 3, 4, 5, 6, 7, 8, that chain is not going to be our parent chain. The parent chain must include the aldehyde, and it must be numbered such that the aldehyde gets the number 1 here. And so this would be carbon number 1, and then 2, 3, 4, 5, 6. So the parent chain here would be hex for 6 carbons and al for aldehyde, hexanal. When it comes to the numbering, as I said, the aldehyde is now our highest priority group, so the aldehyde carbon is going to be assigned carbon number 1. So here we have a molecule that contains an alcohol, an alkene, and an aldehyde. And we're going to choose our parent chain such that it includes the aldehyde, and the aldehyde gets the lowest number here, 1, 2, so 1, 2, 3, 4, 5, 6, 7. The parent chain here would be hexenal, ene here because of the ene. And then this would be a hydroxy group. So if we were naming this whole compound, and this is a little bit more complicated than what I usually ask you to do, but the parent chain here would be the hexenal chain. Our substituents would be, we'd have a methyl group here. This is a methyl. This is going to be a hydroxy group since it's not the highest priority. The aldehyde is now the highest priority. This is going to be another methyl group. And there's not going to be E or Z on this because there's two hydrogens here, so we don't have to worry about E or Z designations because these two groups here, hydrogen and hydrogen, are the same. So there's not going to be an E or a Z. One of these would have to be different. And so the parent chain here is going to be called hexenal, and we're going to have to put in the locates too. So the ene here indicating the double bond, ene. And so now we're ready to write this full name. So we're going to have to indicate the number of the aldehyde here, but the aldehyde's always in number 1, so actually we don't have to assign it a name. We can say now, since the ene is on number 6, we would say 6 hexenal, or we could also say hex 6 enal. Either one of those is fine. I prefer 6 hexenal. And now we're going to number our substituents in alphabetical order. So methyl is going to come before hydroxy or after hydroxy, because methyl is after H in the alphabet. And so we're going to say 5,6 dimethyl, since we have two methyls on carbon 5 and 6. And then we would say 5 hydroxy. And so then we'd have our complete name: 5-hydroxy, 5,6-dimethyl, 6-hexenal. And of course, this carbon here would be a chiral carbon. So if the wedges and dashes were used, we'd have to determine the R and the S configuration. But since the chirality was not indicated, we cannot state it here. The take-home message here being that we're going to start our numbering from the end that has the aldehyde. And the aldehyde will always be on the end, there being a hydrogen attached. So we'll always get number 1. And that's why we didn't have to say hexene1al. With aldehyde, we don't have to indicate the location. It's always number 1, unless it's not the highest priority group. Ketones are very similar, except ketones can occur in various places in the middle of the chain. So we do have to use a locant to indicate the location of the ketone. Butane here again, hydrocarbon with 4 carbons, hence the but for 4 carbons, ane for all carbon single bonds. But here this is butane, but it has on the second carbon here, it has a carbonyl group, making it a ketone, so we would call it butanone. The an here indicating that there's no ene, otherwise we would say enone. But it's anone since all of the carbons here are single bonded to one another. The ketone here must be included in the chain. It's going to be a high priority group. The carbon and the carbonyl needs to be given the lowest number that is possible. So when we're numbering this one here, this has got 7 carbons, and we're going to number it starting from the left. 1, 2, 3, 4, 5, 6, 7, not the other way around, 1, 2, 3, 4, 5, 6, 7, because that's going to get us to the ketone first, whereas if we went this way, the ketone would be numbered 5. And after that, we have assigned our locant. The parent chain has 7 carbons, so it's going to be heptan, hept for 7 carbons. The ending is going to be -one since we have a ketone, and the locant here is 3. So it's going to be 3-heptanone or heptan-3-one. Either of those are acceptable. Don't forget that if you do have a chiral carbon and the chirality is shown, you do have to indicate the chirality as R or S for each of the chiral carbons that exist. So don't forget to do that. So let's break down the name of this here. So remember that the parent chain has to include the aldehyde. So the parent chain cannot be the benzene ring in this case, because that would not include the aldehyde. So the parent chain is going to be this right here. And so that's got 3 carbons, 1, 2, 3. So that's going to be called propanal. and because all of these carbons have single bonds, al because it's an aldehyde. Now we're going to have several substituents here. We're going to have a phenyl group as a substituent here, and a chloro group as the substituent here, chloro. And since this is not the benzene ring, we don't name it benzene. We name it as a substituent, and a benzene ring as a substituent, as we previously mentioned, has the suffix phenyl. And so now we're ready to write the name. We would end the name here with propanal. So this ending here will go right here, and then the chloro is going to be listed before the phenyl in the name because C comes before P in the alphabet. So we're going to number our carbons like this: 1, 2, 3. So on the third carbon we have the phenyl group. So we're going to say 3-phenyl. So this is 3-phenyl. This part right here is going to go right here. Remember, this is a mistake I saw on some of the exams there, is that people forgot that numbers never touch letters. There's always a dash between numbers and letters. And if you have to indicate more than one number for multiple substituents, you put a comma between the numbers. But there's always a dash between numbers and letters, as you see here. We have the 3-phenyl, and then on the second carbon we have the chloro, so this is going to be 2-chloro. So that's going to be this part right here. And now we have to assign R or S, and so we can break this out here. And if we look, I'm going to break this out on the side. So we've got on the dash, we've got the chlorine. That's going to be group number 1. That's going to be the highest priority group, having the highest molecular weight. On the wedge is going to be hydrogen, which is going to be number 4, the lowest priority. And then in terms of priority, these two up top are going to be tied, but they have this one, so they're both going to be carbon, but this one has a double bond to oxygen, which is higher in molar mass than the hydrogen. So this is going to be number 2, and this one will be number 3. And to assign R and S, we do a double switch. So we switch 1 and 4, we switch 3 and 2, and that's going to give us our double switch now. And we redraw this now, or I'll put it over here. And so that's going to put the 4 on the dash, which is where we need it to assign R or S. Number 1 is going to be on the wedge, and then 2 will be on the left, 3 will be on the right. And now we're going to have 1, 2, 3. That's a clockwise right-hand turn on the steering wheel, and so we get an R designation. We could say 2R here because it is the second carbon that is chiral, but you only really need to do that if there's more than one chiral carbon. If there's only one, then it is obvious that it is that one chiral carbon that you're talking about, so you can simply say R. There are some kind of weird common names here that can be used. If you have an aldehyde that's attached to a ring, it can be named carbaldehyde, like we here. So we have cyclohexane carbaldehyde. So that's another name that can be used here. And then there are several other parent names that are recognized by IUPAC, including formaldehyde here. So normally this would be called formaldehyde, if we named it systematically, would be called methanal, meth for one carbon, anal for aldehyde. But very commonly formaldehyde is used, and you'll see that on bottles and everything. Here this would be called ethanal, eth for 2 carbons, and al for aldehyde. But often it's called acetaldehyde. And then benzaldehyde here would be the parent name. Instead of, you could say phenyl methanal. But no one says that, actually. This is one you should probably never say. You should always use benzaldehyde. Everyone does this. This is a very common parent name, and it's what should be used. And so that's the nomenclature of aldehydes and ketones. And so, it just kind of follows from what we did before, but we're kind of just expanding upon that. Now, we've learned about a number of reactions that create carbonyl groups, primarily by the oxidation of alcohols, although there are several others as well. And so when it comes to the oxidation of alcohols, We talked about this in chapter 12, so that was a part of Chem 212. The mechanism was not specifically stated for these, but if we use a soft reducing agent, like one called PCC or DMP, these are two soft oxidation oxidizing agents in dichloromethane as a solvent, we can get an oxidation to an aldehyde. Primary alcohols will be further oxidized to carboxylic acids if we use a strong oxidizing agent. And remember, when we mean by strong oxidizing agent is like sodium dichromate in acid or chromic acid, or potassium permanganate, these being strong oxidizing agents. If we use those, you're going to oxidize all the way further beyond this. So if we used, let's say a KMNO4 or something, we would oxidize further and get the carboxylic acid. But if we just want to get an aldehyde, we should use a soft oxidizing agent such as these. Ozonolysis will produce aldehydes and ketones. This will involve the cleavage of a double bond to produce a carbonyl where the double bond was. So again, this one is one where the mechanism is not fully elucidated, but essentially what you do is when you have ozone and then you subsequently use dimethyl sulfide for the further oxidation here, you basically split the bond and you get a carbonyl right here. So a lot of times people look at it as a split with two little eyeballs on either side, and then you ultimately get the two aldehydes here, or it would be a ketone if there were a carbon atom over here. So you'll cleave the double bond, and on each carbon that was in the double bond will end up with a carbonyl. And this was first presented in the alkenes chapter 8 in Chem 212. And a full mechanism was not provided here. A kind of partial mechanism was. But I don't expect you guys to memorize partial mechanism. There's not a lot of utility to that, in my opinion. Hydroboration-Oxidation of terminal alkynes. So if we do this with some kind of alkyl borane here, followed up by a second step with hydrogen peroxide and sodium hydroxide, this is hydroboration-oxidation. If you do that to an alkyne, you'll get an enol, and that enol will tautomerize to an aldehyde. This will be so this produces an anti-Markovnikov hydration. And so remember that this goes through an enol type of intermediate. This is directly analogous to doing a hydroboration oxidation on an alkene, except instead of getting an alcohol, you get a so-called enol. And so you have a double bond here, and the alcohol is attached to the less substituted carbon here, and this enol will tautomerize. This was called the keto-enol tautomerization, and this is a very important process. The mechanism for the hydroboration of oxidation of alkynes was not completely shown. It was shown for alkenes, and you should understand that mechanism. But for alkynes, that full mechanism was not shown. But the mechanism for the acid, and in this case the base-catalyzed keto-enol tautomerism, is shown, and you ought to be able to duplicate that mechanism. If you have oxidation of a secondary alcohol, here you can use a strong oxidizing agent like sodium dichromate in an acidic environment. And you can get the oxidation to the ketone. You don't have to worry about it like you do with the primary alcohols. The primary alcohols, if you use a hard oxidizing agent like this, you will get a carboxylic acid, not an aldehyde. But here you could use the soft oxidizing agents like PCC, PCC, and with the dichloromethane as a solvent. That would work too. However, you can use these strong oxidizing agents as well. So it says you can use mild oxidizing agents like the PCC, or you can use strong. Either way, you'll oxidize to a ketone. You can also do ozonolysis of alkenes. Again, this is just ozone followed by DMS. You get the split in the eyeballs, right? And you get the two carbonyls. In this case, if you had carbons attached instead of hydrogens here, this will not be right here, this will not be an aldehyde, it will be a ketone at the end. Again, this is the same section as where we talked about ozonolysis. This could produce either aldehyde or ketone, depending on what is located here. So you can also have other forms of hydration here. So if you use a standard acid-catalyzed hydration, this is going to give you the Markovnikov addition of water as opposed to the Hydroboration-Oxidation. And so this is going to get you an enol, but that enol will have the alcohol on the more substituted carbon now. And then again, you will go through the keto-enol tautomerism. And you'll get, ultimately in this case, you'll get a ketone because the OH group is not on the last carbon here, it's on the middle carbon. So when it gets tautomerized to a carbonyl, you end up with still having the remaining carbon here on the side, and you end up with a ketone. And then a new reaction that we learned in just the last chapter for making a carbonyl is the Friedel-Crafts Acylation. So this is an electrophilic aromatic substitution reaction. You have to make sure, first of all, that your ring is at least not deactivated by a strong deactivator such as a nitro group, or even a weak deactivator like a halogen atom, or if you have a benzyl carbonyl, that will also deactivate the ring. So this is going to go through a halogenated acyl group here, the acyl group being a carbonyl attached to another carbon in the presence of iron 3 chloride or aluminum chloride as a catalyst. You should recall this mechanism. Remember that the mechanism goes through the formation of an electrophile here that is needed to initiate this. We have the AlCl3, and then we have this chlorine here is essentially going to give one of its electron pairs to create a bond, and we end up with this chlorine here that is the carbonyl, and then we have a subsequent nucleophilic attack here, and that nucleophilic attack will result in a bond being formed. That nucleophilic attack occurs right here, and then we have these groups leaving, and then you ultimately will get this carbonyl here. And of course that goes through a sigma complex intermediate that stabilizes the intermediate and ultimately recovers the stability of this benzene ring. Remember that benzene rings do not generally undergo addition, but they can undergo substitution with the right electrophilic catalyst, or we also talked about how in some cases you can have a nucleophilic aromatic substitution instead of an electrophilic one. You use a nucleophilic reagent, and it goes through a slightly different mechanism with a so-called negatively charged Meisenheimer complex, as they call it. So in terms of nucleophilic addition reactions, the key idea here, so in terms of the reactions that carbonyls can undergo, so those are the reactions, we just finished talking about the reactions that produce a carbonyl, and that was all review from prior chapters. What's going to be new now, and not completely new because we've seen some of these reactions before in chapter 7 when we talked about SN2 reactions, we're going to see that we're going to get a lot of SN2-like reactions, like what we saw in Chapter 7. And the reason why is because the carbonyl here has a very polar bond in the carbon-oxygen bond. In addition, this bond is stabilized. This structure is stabilized by resonance. Here we have, when we have a carbonyl, we have a pi bond between two atoms of differing electronegativity. Calling back to our 5-arrow pushing patterns from Chapter 2. That was one of them, a pi bond between two atoms of differing electronegativity. The oxygen has greater electronegativity, so we could say that the pi electrons are spending a little bit more time on the oxygen atom. And this really represents this charge separation that we've got. So by resonance and also by induction, by the strong electronegativity of oxygen pulling electrons towards itself, the region around the oxygen is quite partially negative charge, and the region around the carbon is quite positively charged. And we can see this very clearly if we look at the structure in mole view. So I highly recommend, when you're kind of considering, when you're thinking about these reactions, when you're looking at a simple molecule and you want to understand where's the positive part, where's the negative part, you should be able to do that theoretically. But it's not a bad idea to kind of confirm it and just take a look at what that looks like. So if we have this guy right here, acetone, what we were just looking at, and we look at its 3D structure here, we can see that big, first of all, the shape where that oxygen sticks out relative to everything else because of the trigonal planar sp2 hybridized carbon. But also that results in a huge charge separation where it's very negative up at the top and very positive over down where the carbon is. And you can see that if you do JMOL electron surface lucent, and you can see that where the oxygen is, it's so very negative. It's very deep red, indicating a great negativity there. And on the other side where the carbon is, it's very deep blue, indicating a very positive charge, and the green is neutral in between. And so we can see we have this huge charge separation, and so that makes the carbon a great electrophile here. The electrons are going to want to come in and attack this carbon, and that's a key defining feature of reactions of carbonyls, is that the carbon here is a great electrophile. It really attracts electrons. So if we have some nucleophile here that's attracted to that positive carbon, it's a pretty wide open for attack too, because of the trigonal planar geometry of the carbon. You have this whole area here where nucleophile can attack from the top and also from the bottom very easily. There's not a lot of steric hindrance here, these R groups being, this whole thing being flat. There's a lot of room for this nucleophile to come in and to attack. And so then we get a new sigma bond in exchange for the CO pi bond. And then if we have a neutral carbonyl here, we're going to end up with a negative alkoxide ion, which would then probably be subsequently protonated by anything that is even weakly acidic. Or even water, for example, would be in equilibrium here with this, about the same pKa water for the protonated alcohol here. Aldehydes are usually more reactive than nucleophiles to ketones, and it makes a lot of sense why, right? You can think of the steric effects. If you have a hydrogen group on the aldehyde, that frees up a whole avenue of attack here on the right side of the way this structure is drawn, where the hydrogen doesn't really get in the way. So you have a lot more access to this positive carbon on an aldehyde. So that really speeds up aldehyde reaction as a electrophile or an aldehyde reaction with nucleophiles. Also, there's electronic effects. The R groups here, the aldehyde here is going to have a larger positive charge because the carbon atoms here are electron donating. They're of equal electronegativity to the carbon, so by the hyperconjugation, they can donate some electron density here to this carbon, reducing its partial positive charge to a little bit lower of a partial positive charge. So aldehydes are generally more reactive with nucleophiles than ketones are for these two reasons. Some nucleophiles will require acidic conditions, other will require basic conditions. For example, we learned about the Grignard reactions back in the alcohol chapter 12. The Grignard reaction involves a reagent that is a carbanion and a very strong nucleophile, but also a very strong base. So this, if we look at this this Grignard reagent, remember that we can think of Grignard reagents almost as ionic. So here the methyl group here, or I'll just write it as CH3. That's a methyl group, right? This is going to have a positively charged carbon. Negatively charged carbon. It's going to be a carbanion, and we'll have the positively charged MgBr complex. So this is negatively charged. And so that ends up being an extremely strong base. So notice that this reaction occurs in two steps. We add the water after. We can't have any water when we first use the Grignard reagent, because water would definitely protonate this carbon. Remember that the methyl group would have a pKa of like 50. It's a terrible acid, making this methyl group tremendously strong base. And so anything that can donate a proton to it will. But if we have this this methyl reagent here, Grignard reagent, this will also be a very powerful nucleophile as long as you have it in a basic environment and is not protonated, and it can do a nucleophilic attack on the carbonyl here. Now again, note that when we have a nucleophilic attack on this neutral carbonyl, we're going to end up with an alkoxide ion that would need to be protonated. So we can protonate that with anything sufficiently acidic. Even water would be okay. So generally water is followed up, and that will ultimately be in equilibrium with the protonated alcohol here. And of course now we have this methyl group here too, which I did not draw, but now this methyl group is also attached, which is indicated with the Me here. So if we have a Grignard reaction, the methylide ion here is going to be extremely strong, the alkaline ion, or alkyl ion here, but it'll also be a very strong base. So we need to have this done under basic conditions. So nucleophiles that are extremely strong bases include Grignard reagents, hydrides, which is H-, which you can have with like sodium hydride or something. Under basic conditions, we'll have nucleophiles reacting with the carbonyls, but you have to follow it off with a proton transfer, right? So that's exactly what we were showing here. We have the proton transfer, so we have the nucleophilic attack. We end up with a negatively charged alkoxide ion here, and that is subsequently protonated by water with a proton transfer. This lone pair here grabs a proton, then leaves these 2 electrons behind. And so we have a negatively charged intermediate, which we do a workup on after. We say acidic workup, meaning a subsequent step to then protonate this. And at that point, if it were dissolved in a polar solvent, it would probably come out of solution at this point, and then we would filter it and collect it. Also possible is to do a nucleophilic attack under acidic conditions, and in these acidic conditions you'd start with a strong acid that would protonate the carbonyl, and so we'd have a proton transfer here, and this will produce the acid for us. You need a particularly strong acid, very, very strong, such as a hydrohalic acid, sulfuric acid, because the protonated carbonyl itself has a very low pKa, down in the 2s or 1s. So you need something essentially with an acid with like a negative pKa. But once this is protonated, this makes it an even more powerful nucleophile or electrophile. So the nucleophile is going to go in and attack, and then at that point you'll end up with a neutral alcohol. So the carbonyl will start in an acidic environment. The carbonyl will start by being protonated and then followed up by a nucleophilic attack. So one thing that's valuable about this is that it makes the protonation of the carbonyl makes it an even more powerful electrophile. You can think of this almost as being like a good leaving group in a sense, right? It's already protonated. You're not going to end up with a charged complex afterwards. Once a nucleophile attacks. Also, you can consider the resonance here. Again, once this is protonated, so we have the proton transfer, the oxygen is making 3 bonds and has 1 lone pair, which means it has a positive formal charge. And we still have a pi bond drawn here in the Lewis structure between 2 atoms of differing electronegativity, and so we can drew the 1 arrow here, putting the lone pair here on the oxygen. This leaves this carbon with 3 bonds and no lone pairs, giving it a positive formal charge. And so you can see how this is essentially like a full positive charge rather than a partial positive charge on the carbon. So very, very powerful electrophile. It will react with nucleophiles really well. And this is required. So you want to do this if you have a weak nucleophile, you want the reaction occurring under acidic conditions to encourage the attack of that weak nucleophile onto the carbonyl carbon. So when a nucleophile attacks the carbonyl groups, the equilibrium is going to depend on the nucleophile, the way the nucleophile will function as a leaving group here. Okay, so for example, if here we were we're reacting with HCl. So again, remember this is going to go through a two-step mechanism here. We'll have first the protonation, right? So the oxygen here, its lone pair, will grab the proton. Electrons will be left behind, which will then leave you with a chloride ion, and you will have the protonated form of the carbonyl, and then you will have the nucleophilic attack by the chloride here, and then that will produce for you the alcohol. And so you'll have a chloro group here on the alcohol, but the chloride's a good leaving group. So here, in this case, the equilibrium is going to favor the starting ketone rather than the ultimately produced chlorohydroxyl carbon here. And this is because the chloro would rather not be attached. It can leave very easily. Anything that's a great leaving group and stabilizes the negative charge will probably just stay this way. So equilibrium here is going to favor the starting ketone because the chloride is a great leaving group. If it was a terrible leaving group, like if it's hydroxide, then it will favor the product here. That would be a dihydroxyl type arrangement. So as we're moving forward, we're going to consider the reactions of various nucleophiles. We're going to start by talking about oxygen as nucleophiles in this lecture, and then we're going to refer to another number of nucleophiles, including atoms sulfur, nitrogen, hydrogen, and carbon. And so here we have a few examples of neutral oxygen nucleophiles: water, an alcohol, a diol, and then here we have the sulfur dihydride, or dihydrogen sulfide, essentially. We have disulfides here. We have primary amines, secondary amines. We have hydrogen nucleophiles, basically aluminum tetrahydride, boron tetrahydride. Remember from previous chapters that these essentially release a hydride ion. That's the way that they function. The first step here is just releasing this hydride ion for reaction. And then we have Grignard reagents, cyanide ion, any carbanions. These ones are carbanions, these nucleophiles. So let's start to talk about the hydration of the ketones, so the carbonyl here. So as we said, if we have a terrible leaving group, if we have a great leaving group like the chloride leaving group, that will not function well as a nucleophile. Instead of attacking and staying attached to the carbon, it will instead stay leaving the carbon and not being attached to it. But if we have water here, the ketone can react in the presence of water, and it will produce a so-called hydrate, where we're adding on a water essentially to this. In the H2O here, we're going to have the hydroxyl group left, and also this oxygen here will end up getting protonated. So we'll add a hydrogen and an oxygen and another hydrogen. So that's adding H2O. Equilibrium generally does not favor the formation of the hydrate. It's because here, when we have water here, the hydroxyl group here, the water itself would be a decent leaving group. The hydroxyl group would not, but it would leave on its own rather, probably. That would be a little bit more favored than just producing the hydrate here. But it can be done. When it's done, the mechanism here under the basic conditions for this hydration, if you don't just have water, if instead you have a base, this will be a much better nucleophile, and so this can attack under just normal conditions, hydroxyl being a very strong base and strong nucleophile. And so this is going to undergo a nucleophilic attack. Again, remember, this carbon is the positive region of the molecule, so we're going to have a nucleophilic attack to this carbon, and because the carbon cannot have 5 bonds, we have to have another arrow here, which is a resonance arrow that shows the electrons instead located on the oxygen. But of course, that leaves us with an oxygen of 1 bond and 3 lone pairs, so it has a negative formal charge. So after that, it has to be protonated. So we say this is base-catalyzed because this is occurring in water as a solvent. It has hydroxide ions. But when we produce the alkoxide ion here, from the first step, the nucleophilic attack, we're going to then have a protonation from the water, and that will then recover for us our hydroxide ion, right? And so we say this is base catalyzed because the hydroxide ion isn't used up in the reaction. It is then recovered by the end of the reaction. We can also have an acid-catalyzed hydration, and in this case, remember that here, if we're reacting in acidic conditions, for the very strong acid like hydronium ion here, the first step is going to be the protonation of the carbonyl, and so we're going to have a proton transfer where the carbonyl here grabs a hydrogen, and of course the electrons in this bond are left behind, and so we get the H plus moving over, and now this oxygen will have 3 bonds and 1 lone pair, giving it a positive formal charge. And remember that having this protonated carbonyl makes this an exceptionally strong nucleophile. So this is going to drive the reaction with even weak nucleophiles like water. And so the weak nucleophile water will then come in and it will attack the positive carbon. And remember, carbon cannot have 5 bonds, so we should also write this resonance arrow that indicates that now these electrons are considered to be attached to the oxygen. At that point, we have this oxygen here has made a bond with this carbon, which is now making 4 sigma bonds. And this oxygen now has a bond to this carbon, and it still has the 2 bonds to the hydrogen. So it has 3 bonds and 1 lone pair, giving a positive formal charge, meaning this reaction is not done yet. This reaction will continue until the product molecule is neutral and thus more stable. And so we'll have a proton transfer from water. Again, this is occurring in water solvent. And the 2 electrons in the bond from oxygen and hydrogen will be left behind, and we'll get the deprotonated hydrate here. And so this is the acidic and basic hydration of the carbonyl to produce a dihydroxyl group here, the geminal dihydroxyl group. So when you're drawing these mechanisms, remember there's a few things that you consider. You should think about what is the condition under which this is occurring. If when you're drawing the mechanism, if the reaction is happening under acidic conditions, at no point in the mechanism can you sustain anything that's a pretty decent base, because that will be protonated by your acid. They will neutralize each other and no reaction will occur. So you should not have any intermediate that is a strong base in the acidic environment. So if we go back to this example, in the acidic environment, we start by protonating this carbonyl, and this is actually quite a strong acid. Not quite as strong as hydronium, but it is not basic. We're not going to have any base during this whole thing here. Then we have the nucleophilic attack, and finally we get the hydronium back. And so we say it's catalyzed by the acid, by the hydronium. In no situation do we have a base. We don't even have anything negative, right? And likewise, when we have the basic mechanism, it starts by the nucleophilic attack of the strong nucleophile, strong base, the hydroxide. And then we have a protonation by the water, which recovers our hydroxide. So in no situation, and this is strongly basic too, the alkoxide ion. So in no situation here do we have anything acidic or even positive. This would protonate, anything acidic would protonate this alkoxide intermediate, or protonate the hydroxide here and stop the reaction from occurring. Now let's talk about a acetal here. So acetal is what's formed. It's when it's very similar to the hydration, but instead of using water or hydroxide or hydronium, we're going to use an alcohol as a nucleophile. So when you have the alcohol as a nucleophile, you end up having it attached twice and become deprotonated to produce what's known as an acetal. An acetal is when you have a carbon, it's basically 2 ethers on the same carbon atom. You have the carbon atom attached to 2 oxygens, which themselves are attached to other oxygens. And that's the formation of the acetal. This is going to be catalyzed by acid, so generally you use a strong acid that is not very reactive otherwise, such as sulfuric acid, or the even more stabilized sulfuric acid analog, p-toluene sulfonic acid. So in terms of the mechanism here, so for the mechanism, what we've got is, again, this is happening under acidic conditions, so you should be thinking, what happens to the carbonyl under acidic conditions with a very strong acid like sulfuric acid? It protonates the carbonyl. So you don't have to memorize this first step. You should just be thinking, okay, when I've got a carbonyl here, and it's in the acid environment, it's going to get protonated. So we have the proton transfer from the acid here, and that gives us our protonated carbonyl. At that point, remember that this makes the carbonyl much more reactive. So it's at that point that we're going to have a nucleophilic attack here, a nucleophilic attack by the alcohol. And then we use this resonance arrow again to draw the lone pair here on the oxygen. So now this carbon is making 2 sigma bonds. But this alcohol, notice the oxygen here, made a bond to the carbon. It also has a bond to another carbon and to a hydrogen with 1 lone pair. So that gives it a positive formal charge. Now the conjugate base of our acid will then be reprotonated by a proton transfer from the alcohol. And that's going to produce what was known as the hemiacetal here. The hemiacetal. So the hemiacetal is defined by the fact that you have a carbon that has an alcohol group and also has an ether group attached, both. But this reaction will generally move forward and continue in the acidic environment. So if you have a very strong acid, you'll have an equilibrium where you're protonating this alcohol here. And so we have a proton transfer again from our acid here, getting us the protonated water. And at that point, you'll then produce an intermediate here in which the water leaves as a leaving group. So the protonation of the water here makes it into a decent leaving group where it will leave as a neutral water molecule. So at that point, it can leave. And so we draw here a resonance arrow. So we have here this lone pair. And this is going to then be redrawn here as the double bond between the carbon and the oxygen, and then we'll have the simultaneous loss of the water as a leaving group. And so now this oxygen has a double bond here and still the bond to the other carbon, and so we're now going to get this oxygen with a positive formal charge. And at that point, again, recall that when we have this protonated carbonyl like this, this makes this an exceptional nucleophile, so it will attract, an exceptional electrophile. So it will even attract very mild nucleophiles, not strong nucleophiles. So it can even react with alcohols and water. And so we have another molecule, the alcohol here. This does a nucleophilic attack. We have the resonance arrow as well, putting these electrons as a lone pair on the oxygen, and that recovers for us our ether group here. But then we have this alcohol here with this oxygen that it now has 3 bonds and 1 lone pair, so it's positive formal charge. And finally, we recover our acid by the deprotonation, so grabbing the proton from the alcohol, leaving this lone pair behind. And now we have the acetal with 2 ether groups attached to the same carbon atom. And so that's the oxygen nucleophile mechanism for weak nucleophiles like ethers. It must occur in an acidic environment. Remember that because we need that, if we want to work with weak nucleophiles like this, we need this positively charged carbonyl here, this protonated carbonyl, which turns this into an exceptional nucleophile or electrophile that will attract even weak nucleophiles. Acetal formation is an equilibrium process. If you have aldehydes, the acetal will be favored at equilibrium. So if we react this aldehyde here, formaldehyde, with 2 molecules of ethanol, we will get 2 ethoxy groups ultimately attached to produce our acetal, and this will favor the products here. For most ketones, the acetal is not favored at equilibrium, and so in this case, if we react the acetone here with 2 molecules of ethanol here, we can get the acetal, where we have 2 ether groups here, this ethoxy group here, this ethoxy group here, from these 2, but it's going to favor the reactants at equilibrium, will favor the ketone. Now, if we use a diol, the diol is basically 2 alcohols in 1. So both alcohols can react to produce a cyclic hemiacetal. And this mechanism is extremely important, or this reaction is extremely important, because this is going to be the way that carbohydrates make their cyclic form, which is their primary form. So when you have a ketone here with a diol, both equivalents of alcohol come from the same molecule. And so in the first step of the mechanism, you form the hemiacetal with the OH group and then an ether here. And then we have a reaction of the second alcohol producing the second ether, and we get the cyclic acetal. Again, this particular reaction is extremely important for carbohydrates. Now, we may want to control the conversion of this. As we said, going back, there is an equilibrium here. We have slight favors to products in the case of an aldehyde reaction, or reactants in the case of a ketone reaction. But we can control this equilibrium based on our concentrations of reactants and also temperature. So here, if we want to form the acetal, to favor the acetal, what we can do is we can remove the products of the reaction. So remember that each of these is a dehydration reaction. It produces water. So by Le Chatelier's principle, if we remove the water from the reaction, we can drive the reaction forward in order to replace the water that we're removing. So by removing the water product from the reaction, that's one way we can favor the formation of the acetal. If we want to instead go back and undo the acetal, we can add water in. So likewise, if we instead add water into the reaction, the more water we add, the more this is going to drive this reaction to the left towards the reactant product. So we can control the equilibrium here by how much water there is in the reaction vessel. If we're removing water, we can drive the formation of the acetal. If we're making it very dilute and adding more water, we can favor the reversion back to the carbonyl. So that's the acetal reaction. There's one more reaction that we should consider when we're thinking about synthesis here. So if we look at this molecule here, we can see that it has two carbonyls. One is a ketone here, and the other is an ester. Okay, and both of these carbonyls are going to be reactive in terms of these hydration reactions. And so we're going to have to figure out how do we make one of the carbonyls react without making the other carbonyl react. And so let's say we want this carbonyl here to react, but we don't want this one to react, the ester. Well, what we can do is we can reduce the ester first, and then we can oxidize it back again. Okay, or in this case. So we need to convert the ester to a primary alcohol, or rather, sorry, I misspoke there. We're converting the ester here to an alcohol. We want the ketone to stay the same. So how is it that we're going to do that? Well, we can react the ketone with a separate reaction that we just saw and keep it from reacting when we do the reduction here, and then we can unprotect it and and then we'll have our reduced product and we'll retain our carbonyl. So if we reduce this with lithium aluminum hydroxide, we'd end up reducing both these carbonyls. We'd get an alcohol for this carbonyl, but we'd also turn this one to an alcohol, but we don't want that. So we're going to use a protecting group for the ketone. And the protecting group can be created by the use of this acetal reaction. So if we start by reacting this ester and ketone with a diol, we can produce this cyclic acetal, which will not be reactive to the reducing agent. At that point, we can then reduce with lithium aluminum hydroxide, which will turn this ester into an alcohol. And then if we then expose this to a acid and a high concentration of water, we can reverse this process here and ultimately recover our carbonyl. And so that's one way we can protect the ketone if we want to react a group like an ester like this. Remember that the acetal reaction goes through the hemiacetal intermediate, which is difficult to isolate because it will definitely, assuming there are more equivalents of alcohol to react, it will continue into the formation of the acetal. So these can be difficult to isolate, the hemiacetal. But cyclic acetals, hemiacetals, are quite stable, relatively speaking. So they can be isolated here. So let's look at an example of that. Very commonly in carbohydrates, you're going to have molecules that have an alcohol group, and they also have a carbonyl group in the same molecule. This happens all of the time in carbohydrates. That's what makes carbohydrates carbohydrates. So what happens here is that the alcohol group will behave as a nucleophile. So under acidic conditions, again, under acidic conditions we have acid. When we do that, we're going to protonate the carbonyl, which will make it receptive to attack by a weak nucleophile like the alcohol. And then the alcohol will come in here and attack, and then we'll have this resonance arrow here putting these electrons back on the oxygen. So now this oxygen here is an alcohol group. We still have this methyl group. So this methyl group right here, it's still there. That's this methyl right here. And then this oxygen right here is now attached to this carbon. So this bond here is the new bond that was created. And so this is a cyclic hemiacetal. And the cyclic hemiacetals, you'll see these all the time in carbohydrates. These are quite exceptionally stable. So for example, in glucose, there's an equilibrium here between the ringed form, the cyclic hemiacetal, and the open chain form, and the ring form is actually favored at equilibrium. So there's a stability to this ultimate product. And again, it goes through the protonated intermediate in acidic conditions, and then we have the nucleophilic attack. Oops, sorry, wrong direction there. It would not attack the oxygen, right? Negative does not attack negative. Negative attacks positive. So this would activate the carbon here for a nucleophilic attack, and so it would attack right there, and then we'd get a ring. This OH here, that's this group right here, that's this one right here. This oxygen now, that is incorrect. This oxygen right here, I'm just going to do it in green just to emphasize. So this will now be, after this little resonance arrow here, this will be an alcohol. This is this alcohol right here. And then this oxygen is bonded to this carbon, and so we've got this oxygen here, that is this one right here. And so cyclic hemiacetals, the reason why we're focused so much on this acetal hemiacetal reactions, one big reason is because of biochemistry. This closed chain form here, this ring form of carbohydrates, is very common, and we'll see it again when we talk about carbohydrates later in this semester. So that's going to be it for our nucleophilic reactions regarding oxygen atoms and oxygen-containing nucleophiles. When we return for our next lecture, we'll talk about nucleophilic reactions here, or reactions of nucleophiles with carbonyls for other atoms, including nitrogen, sulfur, carbon, and so forth, and hydrogen. So I'll see you in that next video. Have a good one.